So let's tie all this together, shall we? We've learned a lot of different techniques, ranging from deep learning neural networks all the way down to, simple techniques like k-nearest neighbor. These are all different ways of solving many of the same problems, so let's give you a chance to actually try them out. Your final project for this course, that should let you try a lot of these things that you've learned hands-on, is to take some real-world data that I found of measurements of masses detected in mammograms. And we've had multiple real-world doctors look at these masses and determine whether or not those masses are benign or malignant in nature. So your task is to use supervised classification machine learning techniques that you've learned in this course and pit them against each other. Try to predict whether a given mass in a mammogram is benign or malignant based on its measurements using multiple different classification techniques and see which one does the best. All right, I'm going to get you started by helping you to load up the data, but after that, you're on your own. And after you give that a shot, I'll show you my own results just so you can compare them to yours. But this is your big, beefy end of the course assignment. So it's your opportunity to really apply all of the stuff that we've learned in this course so far. Very exciting. So within your course materials, you should see this mammographicmasses.data.txt file. That is the raw data you're going to be analyzing in this final project. If you open that up, you can see what you're up against. It's just a data file of 6 columns of information. And you can see that missing data is represented by question marks. We're going to have to get rid of that missing data at some point, but we'll deal with that in a moment. If you want to see what those columns mean and more information about the data set itself, you can get that in the names.txt file here associated with the data set, and I'll talk you through it shortly too. And this should give you a little bit of an overview of what you're up against. This data came from the UCI repository, by the way. It's a great resource for finding other data sets that you can just play around with and practice with, so check that out if you have a chance. And those 6 columns represent these 6 things. One is called the BI-RADS assessment. That's just a measure of how confident the diagnosis was for this particular mass, and that's kind of giving away the answer, right? So that's not what we call a predictive attribute. So we're not going to use that as part of our machine learning model for training our models. Then we have the patient's age in years. We have a number that represents the shape of the mass, ranging from round to irregular. We have a margin that describes the mass margin from circumscribed all the way up to spiculated. These are fancy words, but an important point here is that even though these are technically nominal data fields, they do have some meaning in their progression here. So we've basically gone from regular to irregular over the course of these numbers. So even though normally you want to avoid using truly nominal data, these aren't entirely nominal. There is some meaning to the numbers that we're assigning to them, so we can go ahead and use them. They're better than nothing. We then have a measure of the density of the mass and the severity, which is the label we're trying to predict, benign being 0 or malignant being 1. All right, so your assignment is to apply a bunch of different supervised machine learning classification models to this data and see which one does the best. So try using decision trees, random forests, KNN, k-nearest neighbor, naive Bayes, SVM, maybe using different kernels, and if you're up for the challenge, build an actual neural network to do this using Keras. Now you'll see that as in most problems, half the data is just preparing your data, so I've given you sort of a guideline to go by here. You definitely don't have to do the exact same steps that I've outlined here. If you want to do your own thing, just open up a brand new notebook and start from scratch if you're up for the challenge. But if you want a little bit more guidance, here's a little outline of the way that I approach this problem. So you do need to start by importing it into a Pandas data frame so you can manipulate and analyze that data. There's the read CSV function you can use for that. And you'll probably want to do that a couple of times because you'll find that there is missing data that you need to deal with, and you need to import column names as well because the column names are missing from the CSV file itself. You then can evaluate the data, take a look at it, use describe to get a feel of how it looks. You'll see there's a lot of missing values. It would be a good idea to visualize the rows that have missing data somehow and convince yourself that the missing data is randomly distributed so you're not going to introduce some sort of unintentional bias by dropping rows that have missing data in them. Assuming that it looks okay, go ahead and drop those missing values and you'll have a nice clean data set to import into your models. Now, some of these models do require the input data to be normalized, so you may as well do that up front. You can use the preprocessing.standardScaler function to do that scaling to normalize all of your data to be mean value of 0 and standard deviation of 1, which will improve the performance of a lot of these models, and in the case of SVM, it might not even run at all without it. Start off by doing decision trees. Again, I've walked you through the basic steps involved here of implementing decision trees on this data. And next you can try SVM with a linear kernel, see how that compares. You can use KNN. There's actually an implementation of KNN in scikit-learn you can use instead of doing it from scratch like we did in the course, so that should be pretty easy to try. The beautiful thing about scikit-learn is that all the models have sort of a common interface, so once you've done one of these, trying different models becomes pretty easy. You can also use the naive Bayes approach to see if that can actually do a better job. And a couple of hints there as to what you need to do. SVM might be worth revisiting with different kernels than linear. That's an example of a hyperparameter, so maybe you need to tune the hyperparameter of which kernel you're using with SVM to get the best results. So try RBF, try Sigmoid, try Poly, see which kernel does best. And finally, if you're up for the challenge, you can try developing a neural network using Keras. Just a plain old multi-level perceptron should do the job here. Shouldn't need too many neurons, shouldn't have to be too deep or too wide even to get decent results. And see which one does the best. You might need to tune some hyperparameters before you're confident in a choice, and the results might surprise you. They're actually, I don't want to give too much away, but you might think there'd be a huge difference between the performance of these models, and in some cases there are, and in some cases there aren't. But give it a shot. This is a good exercise. It's going to take you quite some time. I'd set aside a few hours for this, but it's a great chance to apply everything you've learned in this course, or a lot of what you've learned in this course at least, and see if you can apply it to a real-world problem. If you come back in the next lecture, I'll show you how I tackle this, and you can compare it to your results.